Okay, welcome to today's lecture. And today I would like to finish the treatment of analytical reconstruction algorithms for the radon transform with a lot of remarks. Okay, let me start by some remarks on implementation. And we'll restrict ourselves to parallel sampling again. So this was the definition of parallel sampling. I'm not going to go into detail about that now. And we proved that in order to have an exact reconstruction algorithm, we need to have that Q is smaller or equal to omega over pi, P larger than omega, where omega is the bandwidth of the function f that we would like to reconstruct. Okay, first of all, assume that we're not choosing an omega up front, but rather for an existing computer tomograph, we're given P and Q, so that's the number of directions and the number of sensors that we have. Then obviously the maximum frequency that can be reconstructed is omega as the minimum of P and of pi times Q. So that means let's assume we have an existing CT scanner. Then raising P does not necessarily help us in reconstruction. It does not improve the resolution if pi over q is smaller than p. And on the other hand, if we raise the number of sensors, if we measure more exactly, then that doesn't help if we do not at the same time increase the number of directions from which we look onto the object. So obviously, these two should be tied together, and we should have the optimal ratio P over Q equal to pi. And that's actually something that's used by all the CT scanners which are implemented. Okay. So how about the numerical effort? And of course, in the following, I will assume that this is true. So P over Q has been selected as pi. Okay, so what about the numerical effort? Well, we proved, or we selected the reconstruction formula as follows. And obviously, for every x we have, for every place where we want to evaluate our approximation, we need to perform this double sum over here. So first we observe that f is omega band limited. So the sampling theorem tells us that f should be sampled with a spacing of pi over omega. We have capital O of omega square values, which we need at which we need to evaluate f. And for each evaluation, as I just said, we have to compute this double sum over here. So that's for each omega square, for each of these, to compute one of these values, I have something like p times 2q plus 1 additions. And since both are tied to omega, that means for each evaluation of the omega, the omega convolved with f, we need capital O of omega squared operations. We have omega squared places where we need to evaluate that, so the numerical effort is something like capital O of omega to the 4. That would definitely have been too large for the first tomographs. Probably it would be doable today, but there's a much better idea than to just evaluate the sum over here. And to get that, let's for a second fix theta as theta j. So let's fix one theta j and let's look at what is actually computed over here in the inner sum. Well, in the inner sum, we compute the convolution of v omega and g, and at the place x times theta j. right? I mean, this is the convolution because we've selected everything in such a way that the sum, that the trapezoidal rule is exact. So this is nothing but the convolution of V omega and G evaluated at x times theta j. Now define h of s as V omega convolution with G of at s. So then what we're trying to compute is h of x times theta j for each x at which we want to compute the approximation. Okay, the problem with that is that x times theta j is completely irregular. If we insert all the x's where we want to evaluate the approximation, then this is definitely not equidistant. We cannot use FFT to compute the convolution in a fast way. Excuse me. Well, I got lost. Yeah. It's irregular, so we cannot compute it in a fast way, so that's all very bad. However, since, again, we look at the convolution of V omega and G from the Fourier side, and then this is nothing but the inverse Fourier transform of, Fourier transform of V omega convolved with G. So applying the convolution theorem again, this is nothing but square root of 2 pi inverse Fourier transform of V omega hat times G hat. And since V omega hat and G hat are omega band limited, obviously V omega convolved with G is omega band limited again. Okay, so it doesn't make sense to sample H in a very small detail, but it's okay to sample H just on a grid of resolution smaller than pi over omega, which is 1 over q, if we've chosen q according to our condition from point 1. Okay, so we should sample H on a grid of spacing 1 over q, and SL have the spacing 1 over q. So what we need to do is we need to evaluate H for these SLs. Okay, so let's try to do that. Bad luck today. So if we insert that, then what we need to do is we need to compute the convolution of V omega and G at the positions Sj, and so this is exactly what I have over here. Now, if I do that, I can compute H of S for every S just by interpolation. And that's guaranteed by the Shannon sampling theorem. And of course, we'll have to use the Shannon formula to reconstruct that H and to compute H of S. Now, that would be a lot of effort. You remember the Shannon reconstruction formula. There were these sinks in there. And so in practice, that is not done. But what is done is H of SL is computed, and then H of S is evaluated just by linear interpolation, and it turns out that in practice that doesn't make too much of a difference. And maybe you remember that I showed you the MATLAB code, or I showed you a MATLAB example, and there were actually 2 arguments that I had to provide. I had to provide the filter, that was Ramlak in that case. And the first one was something like linear, and that's exactly this interpolation. So the interpolation scheme that's used, I could also use cubic there, I could use nearest neighbor, but well, nearest neighbor, it turns out that nearest neighbor is a bad idea, but everything else is more or less fine. And so linear is, I think, what is always used now in practice in existing tomographs. Okay, so now let's look at the effort for computing the approximation again. We need to compute these H of SL upfront before we do any approximations. So for each theta, we need to compute these convolutions. So that would be omega squared. Omega, we have capital O of omega values of S, and for each of these we have to compute the sum, which has a length of capital O of omega. So for each theta, we have something like capital O of omega squared as an effort. Well, since this is now all equidistant, we might even use the Fourier transform to evaluate the convolution. And it turns out that we can reduce that to capital O of omega squared times log of omega, right? Because the effort for doing the fast Fourier transform is something like capital omega times the logarithm of omega. But you could also use omega to the 3 here, which would be the straightforward implementation. Now, for each single evaluation of our approximation, what do we have to do? Let me go back to this up here. Well, for each evaluation of the approximation, we'll now have to compute this sum over here. The right-hand side over here has already been computed. That's our h, and we can easily get the values of that by interpolation. So we have for each of these evaluations, we just have capital O of omega over here, so that for omega squared evaluations, we have something like capital O of omega cube. Okay, so finally, the back projection step takes capital O of omega cube. So all in all, we have a numerical effort of capital O of omega to the cube operations, which was actually doable in those times and which is definitely doable today. So it's not only that the inversion of the radon transform is not that improperly posed, it's even extremely fast. Okay, I would like to make one final remark with respect to the Ramlak filter. And maybe I hope you remember that the way that V omega was defined, or we computed V omega as the following function. And I'm not going into detail about this. So this is what I computed in the last lecture. Okay, so now let's put points 1 and 2 together. First of all, according to 1, we have Q equals to omega over pi, and omega over pi. And according to 2, we would like to evaluate the convolution, and that means the V omega of S only for Sk minus Sl, which is Sk minus L or K minus L times 1 over Q, right? I mean, that's the only thing that comes up here. This is the one. Okay, so let's look at what that V omega of SL in fact is. First of all, we had already computed V omega of 0 is omega square over 4 pi square times 1/2. That was by using the continuity. And now let's look what happens if L is not equal to 0. Well, that means that SL is L times Q, which means that S is L times omega over pi. Now I just insert over here, and then we have V omega of SL is omega squared over 4 pi squared. Think of L times omega times Q, which is omega 1 over Q, excuse me. So that's L times omega times pi over omega plus 1 over omega squared SL squared cosine of L times omega times pi over Q minus 1, and that's it. Okay, but now remember, L is not equal to 0, and the sinc is sine x. Sinc x is sine x over x. And this is now a multiple of pi, so that evaluates to 0 for L not equal to 0, because it's something like sine of L times pi over L times pi, which is 0. Now, what about this one over here? Here we have the cosine of L times pi, which is nothing but -1 to the L minus 1. So if L is even, then this over here is 0. And it goes away. And if L is odd, then this is -2. And if I now additionally plug in for SL here, again, L over Q, which would be L times pi over omega, then the omega goes away. And just plugging everything together, we get that for L not equal to 0, the omega of SL is 0 for L even, and omega squared over 2 pi to the 4 L squared for L odd. So first of all, that means that when we evaluate that sum over here, when we evaluate the inner sum over here, this one here is actually 0 for L even and L not equal to 0. And, no, not this one, excuse me. When we evaluate this one over here, then if Sj is equal to Sl, if this is the same as Sj minus L, and if j minus L is 0, then this is 1/2. If J minus L is even, but not 0, then this is 0. So we have only half the sum over here. We need to take into account only half the sum. And we can even give a very simple analytical representation for this if j minus L is odd. Okay, and in fact, this is the definition that Ramlak actually gave in their groundbreaking paper. And so if you happen to look into it, I think they don't even talk about the sinc and cosine and all these things, but really they come up with this definition down here and actually taking a completely different route. And if you look into the definition of filters in the implementations, I think in MATLAB it's no longer accessible, but definitely in Python, you can look at how the filter back projection algorithm is implemented and how the filters are implemented. And then you won't find the sinc and you won't find the cosine, but this is exactly what you will find there. Okay, so these are the first remarks, and we'll continue with something about resolution.